Thank you very much for me and thank you for organizing this workshop. And I have been enjoying for past 2.5 weeks. It's wonderful. Um, so as you see that today I'll be talking angular fractals in permittivity. So it's basically about the possibility of high temperature behavior of different functions in, and for most part of the talk, focusing on conformal field theory, not QFT. But at the end, if time permits, I will mention how and what results generalize to massive QFT. So most of the talk will be about CFT and thermal, I mean energy behavior or the high energy data in CFT. And we will be asking whether there is some universality in this high energy data. So that's the broad goal. Universality. And when I say universality, it means that it doesn't depend on what kind of CFTs we are looking at. It will be characterized by parameters or some set of data. And it will be in D equals 2, and more importantly, and higher DCFT. So the piece of the talk. So first with D equals 2, we have a lot of control because of modular invariance. Then I will briefly kind of results we can D equals 2, and then that will motivate us to ask in the context of higher dimensional CFTs where we do not have modular invariance. But we'll see still we can make some progress and we can have some prediction for high energy universality of high energy data at DCFT. So talk about universality in high energy data in D equals 2. The first example that comes to our mind is, of course, Cardy formula. So in we consider 2D unitary modular invariant. And the Cardy formula tells us that the density of states at very high energy infinity is given by a universal formula. It goes like some power of delta times exponential twice pi p delta over 3 square root. And this formula is universal because this form is universal and only depends on the parameter, which is we call central charge. So once I give you the central charge of the CFT in 2 dimensions, I do not really need to know the other structures of the CFT. It automatically constrains the behavior of density of states at high energy. And of course, like to be more precise, you need to your states over some small interval, and you can make this thing much more precise. But that's a on the day. We'll be mostly focusing on smooth approximation of rho of delta. And if you like, I will be these universal results in the context of canonical ensemble. So another of these results is to consider the torus partition function or the thermal partition function, which we define as trace e power minus beta h. And the way we derive this formula is we look at this partition function in the beta going to 0 limit. And in the beta going to 0 limit, this behaves like exponential 4 pi square over beta c over 12. So again, we see that the high temperature behavior is indeed controlled by a single parameter, which again the central charge. And if you take this expression at the high temperature, if you do an inverse Laplace, then so in this talk, I will in this form where we look at some high temperature partition or high temperature partition function with some insertion of the velocity, and we will be what is the beta going to be zero behavior of those kind of partition functions. So, so just to recall how this thing is derived, is a very basic fact of modular invariance, where we know that z of beta is related to z of 4 pi square over beta. And if we take beta going to zero limit on this side, this infinity, and everything gets projected to the ground state. And that immediately tells me that the beta going to zero behavior will be controlled by this ground state energy, which is given by minus c over 12. And that's how we derive the universal property. And now we know that in the two-dimensional CFT, like we not only have a small transformation, which is just one group element in the PSL2Z, we have many more elements. So in particular, we can define this partition function in terms of modular parameter tau tau bar, which is defined as phi tau L0 minus c over 24 tau bar. And this thing is same as if I do some modular transformation where gamma belongs to this group PSL2Z. Now the idea is that if we use this other modular transformation, we can gain some refined information about density of state or about kind of partition function with insertion of some other group elements. For example, we can ask for example, could have that what is the behavior of, for example, this quantity raised e power minus beta h minus 1 to. So because the expression of minus per j, where's the spin, even spin and the odd spin in a different. So roughly speaking, in the microconical ensemble, the behavior of rho even spin delta minus rho odd spin delta in delta going to infinity limit. Again, this is some subleading information. So here the Cardy formula predicted the density of states for all operands. Here we're seeing how rho even minus rho odd behaves as delta goes to infinity. And this quantity is captured by this in the canonical ensemble, captured by this kind of partition function with insertion of minus 1 to j. And now we ask whether there is some universal behavior of this quantity in the beta going to zero. And it turns out that we can use this other kind of modular transformation to say something about it. So this has been explored in this paper by Nathan, Hiroshi, Ifan, and Shueng. Back in 1999, where this minus 1 to the power j use the following modular transformation, which goes like minus 1, to 0. This belongs to PSL2Z. So this quantity here on this left hand side is given by this parameter tau, which is half plus I beta over twice pi. This presence of real part in half basically that there is an insertion of minus 1 to the power j. And once this modular transformation on tau, tau goes to minus tau over 2 tau minus 1. And if I evaluate the quantity, then I will see it. So once I plug, so the idea is that in the beta going to zero limit, if I do the modular transformation, it becomes twice pi over beta, and again everything gets projected to the ground state. So I can write down a formula for this. which looks like 1/4 4 pi square over beta 3/12. Now, if you compare this formula with formula here, you will see that the universal factor of 1/4 that appears compared to this other formula. So in other, someone tells me that what is the high temperature behavior of Z of beta, that is, if someone tells me the value of the central charge, I immediately predict what would be the behavior of this quantity in the beta going to zero limit. Invariance basically, in some sense, relates this quantity with this quantity in some way. And it's not only true for -1 to the power j, we can do a little bit better. We can take trace e power minus beta h, e power twice pi I, p over qj, where p and q are co-prime to each other. And then the idea is to do a modular transformation, which looks this into a PSL to 0. Once I implement this modular transformation of quantity, I can again take beta going to zero limit, and the answer will be exponential 1 over q square 4 pi square over beta 3/12. And I can also insert e power I beta omega j here. And then the only modification happens here, I have beta times square. And I can write down the Cardy formula also, which is trace e power minus beta h I beta omega j, which in the beta going to zero limit goes like exponential 4 pi square beta 1 plus omega square 3/12. So again, we see that like the effect of the insertion of this operator exponential twice pi I over qj is introduced, is basically manifested in this factor of 1 over q square, which doesn't really depend on the central charge or any other thing. So it's the universal factor. Yes. Yeah, the omega is not rational, right? Yes. Like beta. So the point is these two quantities are kind of different because in the beta omega, I am taking beta going to zero limit. So this rotation is very small, whereas this rotation is a big rotation. So to derive this formula, you use the S modular transformation, whereas to derive the formula that appears upstairs, you use this transformation. Yes, yes. Yes, omega appears here. Let's see. And okay. Yeah. Mm-hmm. 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 Yeah, that's not true, right? I would imagine if you want to do modular bootstrap, then that would like the negativity will spoil things, so you cannot do that. And this is real. And in terms of asymptotics, you are basically probing some leading information. So in the leading order, even and row order are equally distributed. That's like half times Cardy. And this is like some plus or minus the subleading correction. Oh, so yeah, so in 2D, I guess we can still make this, well, as long as CL and CR are same. you can make this claim that rho even is basically bigger than rho. But as you will see in the higher dimension, it's not entirely clear what the sign of this thing is, because there can be some order one term in the effective action, and that can fit. Hmm. But then the bootstrap in the asymptotic sense, I guess. Mm. Mhm, mhm, mhm. Yeah, because yes, like if you pick finite point like that we find and then expand around that, then I think that could be far away from this region because like beta going to zero. So oh, if you want to project onto fixed spin, then that would be a different partition function, do a Fourier, project onto some fixed spin, and then basically do Cardi like trick over there. Yeah. People have done that. Yes. Yes, exactly. So yes. For example, if u becomes of the order of beta, you should not perform it. Right. And no, I sharp statement in the microcanonical because the problem is that there can be oscillations, and once you have oscillations, then it's not clear what would be the size of the averaging window. Presumably, there would be some averaging window over which, if you average, you should get the inverse Laplace of this. But then the problem is that I think that size of the averaging window might not be universal. So once we go from one CFT to another CFT, it might vary wildly, unless you give in some extra input. Oh, I would imagine, for example, in the eyes. That's a good question. No, I would think like if you take, for example, like some rational CFTs, I would imagine that at least for some more than like order one window, like if you have the window size to be very big, then it should work. Yeah, yeah. No, but I mean, if I take some rational CFT and if I can do the sum, like rho even over all the thing, then it should work. Right? Okay, yeah, but yeah, again, the point is that it's safe. It is safest to say things in the canonical answer. Yes, good. Uh, okay, so now the question is that now basically we have seen that there are two kinds of quantities. One is this, and one is this, where we have insertion of some angular velocity, and 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 the important difference is in the beta going to zero limit, this is really a small rotation, where beta going to zero limit, this is a finite rotation. And and we have to do two different kind of modular transformation to predict behavior, the high temperature behavior. But at the end of the day, the high temperature behavior of these two quantities are related to each other by this factor 1/2. Now we ask what happens in higher dimensional CFT. Can we have similar kind of behavior? in higher dimensional CFT. So in the question, we ask what happens in higher DCFTs. Higher dimension, you do not have this modular transformation, like not the S or not this other kind of transformation. But the equation is that because at the end of the day, modular invariance is related to doing manipulation with the path integral. So maybe one can think of this higher dimension as doing path integral over some manifold, and one can play with this, manipulate with this path integral, land up with some universal answer. In fact, like it turns out that in recent times that people have been able to write down some effective field theory, which basically organizes the high temperature behavior of this kind of thermal partition function in the beta going to zero limit. So there is Meenola, Siraj, and other people. And last year, Nathan, Hiroshi, Geha, and David wrote this paper where they write down something called thermal effective field theory. And the main idea of thermal effective field theory is to write down some expansion in the beta going to zero limit, and then there will be Wilson coefficients with this in this field theory. Wilson coefficients will characterize the high temperature behavior. And from that perspective, the central charge appearing in two-dimensional CFT is just an Wilson coefficient in that thermal effective field theory. So now first I will review the ideas that appeared in this paper to behavior of this quantity. And I will ask whether we can write down some effective field theory for this other quantity, and there is some relation between these two EFTs or the Wilson coefficients appearing in this expansion and in this expansion when we apply the thermal effective field theory for higher degree. So the first question is, the first thing we will show that I beta omega j. Also in higher dimensions, we can have multiple cartons. So I can turn on fugacities corresponding to each of carton directions. So there are multiple omega I. And then there will be some expansion here, which roughly looks like with some coefficients. AI beta to the power d minus I. Maybe I should write it. So roughly speaking, it should go like exponential. You will see some coefficients, a beta to the power d minus 1. And each of these terms will come with some coefficients, and which basically characterize partition function in the beta going to zero limit. And then we will be asking, if someone hands me these Wilson coefficients for this effective field theory, can I predict the behavior of this quantity? Where I have some extra insertion of Pi over Qi dot Ji, where these are all rational numbers. And of course, that indeed we can, when you give me this Wilson coefficients for this thermal effective field theory, I can also predict what would be the behavior of these quantities in terms of the Wilson coefficients appearing here. So here I was bit static. Of course, there will be omega dependence. So yeah, it will be clear in a second. Yeah. So in this case, basically you are evaluating the part on SD minus 1 times S1. And Uh, not completely. Give me 5 minutes. Uh, hmm, yeah, and so this idea is the following. You first think of this partition function as evaluate path integral over this manifold sd minus 1 times s1 beta, where there is some twisting happening because as you go along the time circle, you also a little amount which is related to beta omega. And then the idea is that if you have strongly interacting CFE, and if you take beta going to zero limit, basically shrinking this S1 cycle. And so going to zero limit, this should be related to some gap theory on SD minus. So that means I should be able to write down an effective field theory, which is basically a local functional submetric and other things, which only lives on SD minus 1. And automatically, like will guarantee me that there is a, to make this thing more formal, what we can do can replace this SD minus 1 with some manifold MD, D minus 1, MD minus 1. So we also replace. And now on the manifold MD minus 1 times S1 beta, I equip this with a metric G. And the idea is because there is a S1 beta, so I can write down this metric G in a Kaluza-Klein form. So this would be G plus e power 2 phi, some dilaton, d tau, and some gauge field A, which basically related to the fact I have to do some small twisting when I go along the time direction and advance the time by tau going to tau plus beta. Is that clear? Now, basically the idea is this gap theory would be a function of this metric G, which is a metric on MD minus 1. And this phi is also a field of MD minus 1. And then there is this gauge field, which is also a field of MD minus 1. So effectively, this is related to some e power minus S thermal, so which is the effective action. And this is a function of G, phi, and AI. This effective action cannot be arbitrary because we started with a CFT, so it has to maintain some, it has to respect the symmetry that in the on manifold you have conformal symmetry, and it also has to respect while invariance. You can use this while invariance So now the idea is that you start with this S thermal action, which depends on G, phi, and K. And you use the while invariance to rewrite it in terms of S thermal, G hat, 0, AI, where G hat is given by G times e power minus 2 phi. And of course, there could be while anomaly pieces. But the point is that there is, like, we can choose a scheme so that, so we have to evaluate. So when we relate this trace e power minus beta h with this path integral, there is a notion of Casimir energy, and we can choose such that this contribution from the while anomaly cancels with the contribution from the Casimir energy. So the point is this while anomaly term will not matter for writing down the asymptotics of this quantity. Mm-hmm. No, I thought while anomaly, I can choose a scheme so the integral of R is 0 because it's flat torus. It came fact that there is a while anomaly term when you I thought in their paper computed this quantity. Yeah. 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 So in this language, yeah, maybe I should write it down then it will be clear. Uh, so you have this P and then the effective action will look like is thermal is we will have square root G hat and then we'll have terms like minus F plus beta square P1 R hat plus beta square P2 F square, where this F comes from field A, and then there are other pieces. Now in P, basically this comes 1 over beta, and this F is related to, so in 2D, F is twice IC over 12. If I evaluate this S thermal, then it would be twice pi E over 12. There is a 1 over beta, and then there is a twice pi coming from this integral. And then if I exponentiate, then this will give me V goes like exponential 4 pi square over beta C over 12. So from this perspective, the answer really from this cosmological constant. Hmm. Yes, yes, yeah, right. Yeah, but I think that yeah, but the idea is that that constant term will cancel this while anomaly. So effectively, if you are counting operators, the while anomaly piece doesn't really matter for counting operators. So in other words, thing should be written down as e power beta d plus some epsilon naught. And then this thing goes like this plus some while anomaly term. Mm-hmm. Mm-hmm, mm-hmm. Hmm. Yeah, but I think that I agree with. But the statement is that the density of states, the Cardy formula, there is no ambiguity. Like the number. No, let's think about if I just count operators, like if I write down all the operators, then that counting is completely fixed, right? We have Rademacher expansion, and there is no scope of any such terms because I am just writing down words or letters, for example. It's, for example, in 2D. Ah, Yeah. 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 No, term will depend on the yes. Hmm. Yes. Yeah. Yes. 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 Yeah. Another way of saying this, that if I have this like if I choose a scheme in the for fixing this while anomaly, then I should use the same scheme to compute the epsilon zero. And yeah. And so for the rest of the talk, it is assumed that that scheme is maintained. Like whatever I do on the while anomaly, the same appears in epsilon zero. Okay. And in fact, if I turn on the angular momentum here, then answer would so I can so here I'm evaluating it for any manifolds with this metric G, but now I can choose SD minus. I choose my MD minus one to be SD minus one, and I can choose the round, and I can evaluate this expression with respect to the SD minus one. And if I do this, then I will get some expansion of the form exponential. If I remember correctly, this would be F times volume SD minus 1, the power D minus 1, product 1 minus omega. This times F over beta to the power D minus 1, and then there will be D minus 2 times beta to the power D minus 3, T1, which is the same here, uh, D minus 1, omega I square, and so on. So the important point is that, like, once I hand you over a CFT, all these coefficients AF, C1, C2, they are given. And then you can put your CFT on any manifold which has a Kaluza-Klein, where the metric can be written down in this Kaluza-Klein form. Then all we have to do is to evaluate this R hat, AF, and all these quantities for that given metric, and I will get an expansion of this form, which only depends on this AF, C1, C2, and so is that clear? Not that I know of, but yeah, 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 yeah. In general, yeah, yeah. They do have a paper, right? But I don't have anything intelligent to add. Uh, well, if you insert -1 to the power a for other like turn on some global symmetry twist, then the f can be negative also. For example, being this quantity, but then imagine you insert some other like there is a some global symmetry here, and then that shape would be possible. Oh no no, yeah. Yes, because yeah, on a physical ground we expect that number of things will grow. So yeah, no, well no, there are yeah. Wait. I think the unitary argument is too quick because this is a beta going to zero limit. Like, wait, no, f can be zero also, no? Well, it's not. Wait, it can have subleading behaviors, right? Even if I remove this term, yeah, yeah. Yeah. Mhm. So this f is the expectation of the stress energy tensor in this manifold. Like, yeah, then no, if it's the spatial manifold, then integral will change, but this coefficient is an intrinsic CFT quantity. So you can think of them as like some density, basically. So one of the power of this effective field theory that you can change your manifold, but still it will be controlled by the same F. You just have to do this integral on a different manifold. Yes. Yeah. Mm-hmm. 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 Yeah. I would have thought as long as there is a gap, you can use this specific field theory. Mhm. 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 Yeah, 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 yeah. Yeah, but there you also have, yes, there I guess you also have zero modes and other contributions, right? Yeah. But here, yeah, here in a, yes, exactly. There would not be any more, so there is the gap and you can write it. Well, I guess EFT is a sophisticated version. Uh, great. So now, so now the point is we understand this. The field theory, it basically captures, like using this, we can compute quantities like trace e power minus beta h, e power minus I beta omega j. But now we look at the quantities of this form, or in particular, I want to look at e power beta h twice pi I u over q ji. So the first nice thought would be that, like, I can, whether I can replace beta omega with pi over qi gi, but that's wrong because uh, in beta going to zero limit, in this quantity, when we trace e power minus beta h, e power I beta omega j, in the beta going to zero limit, this is a very small rotation, as we are trying to probe some big rotation, which is u here. And you see this expansion. So this expansion has a, in the omega variable, this has a pole at omega equals r. So, so basically, want to express, if you want to use the same thermal effective field theory to express this quantity, the same kind of expansion, completely wrong. And you can immediately see this in 2D, where you can see I have written down those answers. Get back the formula. So this is to point out that these two quantities are very different. You cannot use this expansion to express this quantity. So you need to invent some new field theory, or to put it differently, we should that we'll be using the same thermal effective field theory, but we will be evaluating this thermal action on some different method. Yes, yes, exactly. So in we are using different modular transformation, and in hierarchy, the idea is we are evaluating the thermal action on some two different manifolds. And now I am going, like, in which manifold you are particularly going to evaluate this thermal action to get behavior for this quantity. So so right, so till now I have been talking about bosonic theory. So where P over Q is less than 1. Bosonic theories, you can extend it to P over Q to 2. And then you should be think, like, whatever I'm going to tell you, you should be thinking of this group element as a group element of the spin group. And then there will be an appropriate generalization of whatever I'm going to tell you. Mhm. Mm-hmm. So we will not be over rotating the manifold. Rather, like if there are fermions, we will be keeping track of -1 to the power f, and give you so if you have a fermionic theory, then the idea is that there are two sets of Wilson coefficients, one without the insertion of -1 to the power f, and one with the insertion of -1 to the power f. And once I have these two sets of Wilson coefficients, I can evaluate all these kind of quantities with or without -1 to the power f. And in this way of phrasing things, you can put P over Q between 0 and 1. Yeah, sorry. Yeah. Yes. And if you want to view this in a unified way, then you can also view this in terms of then power I -1 to the power f. So on. Yes. Mm-hmm. Yes. I think one of the motivation is definitely to understand the analog of invariance, like what are the analog of these other transformations. And in some sense, it is giving you more and more refined and subleading information about the density of states, because you can add and subtract. But then, well, you might be tempted to say that if I evaluate for all P over Q, I can add and subtract and get the density of states, but that's not true, because some point this will break down, as Lawrence was saying, that the Q will start complete with beta. You cannot use after that. A bit much. I think I am doing terribly with time, but we want to see. Let's start. So, so now I will go back to 2D, and the idea is to derive those two equations in 2D, not by using the modular invariance, by rather using some other this thermal effect technique. And then once I explain the you get that immediately generalized to higher dimension. So for simplicity, let me take -1 per j, where P over Q is half. So we are looking at this quantity. And this quantity is same as doing a path integral over some torus, which looks like this. And so this is beta. Say this is L. And I divide it into two pieces. So the insertion of -1 to j means that we are doing a path advanced by tau to tau plus beta. So this line, this piece is identified with this. This piece is identified with this piece. And these two pieces are also identified because we have a circle. So this is the path integral description, doing a path integral on this manifold with this kind of identification. And is to realize that these two things are identified, piece off and each other. So let me redraw this diagram. I have this, stack it on top. So this less is beta. And we have the identification here that this thing is identified with this. And these two are identified with this line. So this is double line. This line is identified with this. And then this is identified with this. Basically, we are doing, so haven't done anything. I basically use the fact that there's a path integral description, and I can manipulate my path integral in a useful way. So I base this thing. But now this manifold is in a nice Kaluza-Klein form where length is L over 2. So now I can use my thermal action on this kind of manifold and take theta going to zero limit. So yes. Oh, so right now I am doing S times S. So in 2D, but in higher D, as you said, as you predicted, that yeah, as long as you have this structure MD minus 1 times S1, and as long as MD minus 1 has isometry of this minus 1 to the power, so I can do some Z2 rotation. You can do this. You can play the same game. So now I have to, so in my thermal effective action, so this is like almost like my original thermal effective action. I just have to do this replacement, beta to twice beta and L to L over 2. So my original thermal effective action has a prediction which was twice pi C over 12, twice pi over beta. So now what I have to do, I have to take my beta and make it twice beta and take L and divide by 2. So I do this thing. And this immediately gives me this 1/4 factor, 4 pi square over beta P over 12. And that's precisely the 1/4 factor we obtained over there in over Q was half, and I had a 1 over Q square factor. So, and you can see that if I have P over Q, then I have to basically take my torus and take it, break it into Q pieces, and I just have to stack on top of each other. And if I would do that, then basically I will again have L going to L over Q and beta going to Q beta. And again, you can see there will be a factor of 1 over Q square. Yes. No, that's not that. Yeah, that's this viewpoint is more useful because in higher dimension you will have more terms, and for each of those terms, this I will be applying this transformation. Yes, pretty good. Yeah, yeah. Yes. So the yes, exactly. So I was going to say that. So the point is that the is a holonomy because there is a weird identification. Well, not weird. I mean, like strange identification. And if CL minus CR is not equal 0, then you will be sensitive to that holonomy. And in other words, and in higher dimension, I think if you write down the non-perturbative terms, then the non-perturbative terms can be sensitive to this holonomy. So in 2D is just a cosmological constant term. So this is just this piece. Yeah, then you have to, yes, and you have to add some extra term which looks like A times twice pi ik over q beta. Yes. 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 Exactly. Yes. Yeah. Yeah. So in other words, I think like so. Well, I was going to say that. So the point is that here I am well effective and writing down a metric in the Kaluza-Klein form, but there is really a data, and that data is the holonomy, this integral of A, and we for that part. Yes. 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 Okay. So in higher dimension, whatever I here goes through, And so if you look at the leading piece here, beta becomes q beta. So I will have f over q beta to the power d minus 1. And this volume of sd minus 1 also 1 over q. So there is a 1 over q. So that basically means the leading answer will go like 1 over q to the power d times whatever we had from before. So there is a volume sd minus 1 to the power d minus 1, and it will come with this in the leading order. That's the answer for any higher d50s. The 1 over q square factor just becomes 1 over q to the power d. Yes. Mm-hmm. Mm-hmm. Yes. Now, yes. So formally, what happens is the following. So the stacking procedure can be thought of. So this procedure can be thought of as evaluating partition function in this manifold, which is sd minus 1 times s1 q beta, and then you quotient by zq. And this action zq is a part of the rotation. So if you take some n hat, the unit sphere tau, the zq acts like it rotates the n hat, the unit vector, and advance the tau with tau plus beta. So height of the stacking is same as saying that you are basically evaluating the thermal effective action. So you are basically doing a path integral over this manifold with this ZQ action, and the thermal effective action is a way of saying that I should be able on this base manifold, which is SD minus 1 plus ZQ. Yes, now, yes, you are okay, good. So in 2D, of course, there is no fixed point because it's S1, but of course, if you go to 52, then there is a point and the north pole and the south pole. And that means that we should, so another way of saying this is that this action is smooth, but this is a non-bundle over this d minus 1 slash zq because of this action. But when I am writing down in this form, I am forgetting that this is a non-trivial bundle. And so there can be fixed points, and then you have to write down some another effective field theory, which has support on this higher co-dimensional object. But note, because they are higher co-dimension, they will be subleading. They will always give a contribution which is subleading to this behavior. Yes, they contribute to the same order as well. Yes, exactly. And those will be genuinely new information in the higher D that we have in 2D. So in D equals 4, yes, it would be a lens space. If so in D equals 4, you have two cartons, and if you have both the QIs are same, then it will be a lens space. And if the QIs are different, then there will be defect again, and you have to write down some defect action. Then it will not be smooth. Okay, so maybe I should use the other board. Yeah. So in other words, what we derived is the following thing: the minus log of trace. And also one more point that here I have drawn is with a square or a, like there is no small twisting, but you can always slightly slant it and some e power I beta omega j, and the argument goes through in the same way. So you have trace e power minus beta h, e power I beta omega j, and then say you have some group element R such that R to the power q is 1. So this R can be any rotational group element inside the rotation, so that R to the power q is 1. And then this is related in the beta going to 0 limit with 1 over q to the minus log trace e power minus q beta h I omega j plus. So this is the prediction that comes from this manipulation. The terms that appears in the usual thermal effective action, they gets multiplied with, like the beta gets multiplied with q beta, and then there is a 1 over q factor. Plus there could be corrections coming from these defects. And there could be terms in the defect action which can compete with the subleading terms. And then there could be terms which are topological in nature, which captures the fact that this bundle, which we call EFT bundle, is over SD minus 1. So, and there are some, we can do some minor modification of this equation. For example, I can insert some X global symmetry U here, and then basically by the stacking argument, as you advance your time direction by beta, you act by 1 of U, and here basically you are stacking q pieces of them. This side you will have an insertion of U to the power q, and this U can be any global symmetry. Yes. Yeah, yes, right. So we haven't really completely explored like all possible topological terms that appear. So some of them I think in probably Loga's paper, and yes. So the one thing that we have concretely done, like mentioned thing that I mentioned to Lawrence, if CL is not equals here, then you can clearly plot the topological term. Yeah, in the okay. So I mentioned about the topological space. So now I want to make one more comment with focusing on this S defect, is that just to reiterate that if I have fermions in the game, then I need to be a bit more careful about insertion of -1 to the power f. And I also need to be a bit more careful that, so suppose suppose q equals 2 and I am stacking two of them together, and that means -1 to the power gets applied twice, and then it becomes a periodic boundary condition. So whenever you are applying this idea with the fermions, you have to be very careful about how the -1 to the power f acts and track it down. If you track it down, you basically can write down a similar formula. The basic idea is simple. And if you want to interpret in the trace the same way, then basically what you should do, you can write the same formula, but instead of using R to the power q to be 1, you have to use to the power q to be -1 to the power f, and there will be an insertion of -1 to the power f. So there are two ways of saying the same thing. Either you view R as an element of a spin group, or you keep track of -1 to the power f everywhere in your calculation. And once you do this, basically this works out in the same way. Okay. Now I will focus on this action. Uh, this is really a new feature in high dimension that doesn't appear 2D, and there, and again the effective field theory, the power, like on what kind of terms we can write down on S defect. So so the so the first point is that if I am in an even dimension S2 or S4, then I can always arrange for a situation so that there is no defect. For example, in 4 dimension, I can go to a length space. In 1D, there is no like any rotation, there is no fixed point. And if there is no fixed point, then this 0, and then there is no information, and I can all the things if I know the usual thermal effective field theory, the Wilson coefficients appearing in the usual thermal effective field theory. Yes, yes, yes. Like yeah, and another point is that if you are in odd dimension, then whatever you do, you will always land up with some defect. For example, S2 times 1, you will always North Pole and South Pole, which and and the idea is that if you want to write down a action which has a support on the defect, you basically use the same kind of idea. Like instead of SD minus 1, you basically start with some arbitrary manifold M, which has the isometry, so that you can do this quotient. And then you keep the M with some metric and write down the metric in the Kaluza-Klein form, and use the same kind of ideas about reducing it on this manifold, which is M plus ZQ, and write down all possible terms that is consistent with the symmetry. And here again, you have to be a bit more careful because this bundle is non-trivial. So that means there can be other topological pieces, and then it will contribute to this S topological here. So once we do exercise, at least for S2 times S1, so say we do it. So basically, we are looking at S2 times S1 Q beta ZQ. Then there will be defect on the North Pole, South Pole. And once we do this procedure of write possible terms, then we'll see that the defect action can have contributions from a constant piece. This is so there will be a constant piece in the effective action. Then there can be terms which are Hodge dual of this F, where that comes from the Kaluza-Klein reduction. There is a gauge field A, and that E gives you F, and this Hodge dual of F evaluated at the North Pole and South contribution. And you can also evaluate this Ricci scalar R hat on 2 points, and that will also give you some contribution. Once we evaluate this on this geometry on the North Pole and South Pole, you will see that the contributions will go like, so dP over Q. So there will be a leading contribution. So this is the North Pole, and then there is a South Pole contribution with a different orientation over Q. Here again, I have written down this form to emphasize that these Wilson coefficients only care about this P over Q ratio. So if you choose ratio, then these Wilson coefficients will change. And P over Q has periodicity of 1 for bosonic theories. So for example, if I set P over Q to half, then these two quantities same, because half minus half are same for a bosonic theory. Then there will be contribution which goes like Q beta omega over Q A1 P over Q minus A1 minus P over Q. So this comes from this kind of terms. And then you can write down further contributions, which will look like Q beta square over Q which will come from this r hat term, and they will look like some 2 plus 10 omega square a2 p over q plus a2. For example, you can also have term which is star f square and so on. And all this data will accompanied by Wilson coefficients, which only depends on the defect ratio, this p over Q ratio. And for the fermionic theories, this p over q has a periodicity of 2. You should be viewing it as a group element of the spin. Okay. So one more thing to say here, for example, like as I was saying that because p over q has a periodicity of 1, if you set p over q to half, then this term should not appear. So that means if you take any on S2 expansion to see any term which goes, check like you take the 3D free scalar CFT, and then basically you do this thermal effective action, like you basically write down the plethystic exponential and you expand, and you can indeed check that doesn't appear in the field. Okay. And in higher dimension, a lot of other things can happen. For example, there can be multiple defects. So you have down the effective field theory for each of the defects. And this higher codimension intersect with each other and create further higher dimensional defect. And to write down, you have to look possible defects that can appear with various codimensions. And for each one of them, you have to really figure out what kind of terms that can appear in the effective action and then just evaluate it. Is that clear? And for all of these results, like so one thing we did, we basically, we can take free field theory for both scalars and fermions in all the we have presence of zero mode, because I assume that is gapped. So if there is a presence of zero mode in the free scalar field theory, you can turn on some other global symmetry which kills the zero mode. And then you can ask whether then you can basically write down some plethystic exponential and expand it in the beta going to zero limit in a clean way. And basically from that, you can check whether the beta to zero limit has the form that is predicted by this equation. And it matches as it should. Yes. Mm-hmm. Mm-hmm. So here the Wilson coefficients depends on P, for example, in the defect, but in this term independent of as long as there is there can be topology, this can be sensitive. This piece there is no P dependence. So for example, in 2D, the one I wrote down over here, there is P dependence. If you have CL minus CR non-zero. Oh, you mean the non-perturbative correction? Yes, in the non-perturbative corrections there. So there are a couple of things. So the point is that here we are writing it in this, but here you see that some of the terms from this expansion, perturbative expansion, can actually compete with SD or S topological. So whatever terms you were talking about, the P dependence will be in this S topological or in the Wilson coefficient of S defect. Oh, sorry, it didn't. The S topological is the following. So let's go back to the 2D case. So in 2D, I have say S1 times S1, and I am doing minus 1 to the power j. So basically, I have tau theta, which goes to tau plus pi. So naively, you can write down the metric on this thing as d tau square sorry, I mean dt square plus d phi square. But that this Kaluza-Klein form of the matrix will not see this identification. And another way of saying this, that if you have to cover this manifold, you have two patches, and there will be transition function. And that means that you have to specify some holonomy of the gauge field along this cycle. So that's some extra data. And then there should be some extra term in the topological in the effective action which are sensitive to this extra data. And those terms are basically some topological terms. For example, in 2D, it looks like exactly like Simmons term. And those terms will be sensitive to, for example, P. Because so the information of the P comes in this holonomy, like in this identification, basically. But locally everywhere it looks it doesn't depend on P. Sorry, well, I'm back. So there is a F term which comes from the smooth part of the gauge field, but then you're evaluating the F term on this manifold. But yeah, that's not what I'm calling topology. Oh, well, yeah, that's not what I'm. Yes, I see. Yeah. Next, I mean that something that can detect the non-triviality of this bundle. No, the integral. No, so the point is integral of f over this manifold. Like I'm only base manifold that cannot detect whether I have this identification or not. Yes, yes, yes. Yes. Yeah. Does that answer your question? So, okay. How am I doing with the time? Okay, I probably do not need another 2 minutes. Uh, what else? So, okay. So, to okay, make some comment about holographic theory. Before that, yeah. Well, the fractals really comes from it's in the following sense. So in 2 dimension, if you the modular forms, then they are for every rational number in the upper half plane, you have some cast. So there will be some behavior like this. Here also, basically, this P over Q, these rational numbers are like cast. So you have some behavior. But now you can play this game that suppose instead of P over Q, you have some irrational number. And then you have to approximate that irrational number by some rational for Q. And there will be some difference between the rational approximation and your actual number. And that difference can be thought of as some insertion of for I beta omega for some beta. But now the point is you take beta going to zero limit, at some point that approximation will be a bad approximation. So you have to do a better approximation of your irrational number. And so you will have some behavior. So for example, if you just take some toy function like this partition function and plot it for arbitrary angles, you will see like some factor like casting behavior. That's all about angular. And yeah, it depends. It slightly depends on the which irrational number you pick. Yeah, but the point is that if you make a bad approximation, then it will be so. difference between P, like suppose you take a irrational number and you approximate with some P over Q. And the idea is that if the difference is very small of the order of beta omega, then when you plot in some range of beta, it will be captured. You can hope that it will be captured by some Q. But then as you tune the beta to be smaller and smaller, at some point it will not be a good approximation. Then you have to choose some different P over Q, and it will hop to the different EFP. And then there are irrational numbers for which it will never work, because it's like probably Nathan tried it with the golden ratio, I think. Yeah. 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 Okay. Yeah, you can just plot lines in that in the mathematical recipe. And so two more comments. One comment is about holographic theory. In the holographic is basically you would expect the same thing will work. And so what you have to do, you have to, so the idea is that when you compute the partition function without this quotient, basically the black hole solution, and you just have to take that solution and quotient by this thing. And so basically the radial direction goes up the right, and in the other direction you basically do this quotient, and then you get a solution. And if you evaluate the action on that solution, it will just reproduce for you this trace e power minus beta. One subtlety is that, for example, you can do it in ADS3, CFT2. Basically, you will take the BTZ solution, do this, and then because there is no fixed point of this ZQ on this base manifold, so it's all fine and the solution is smooth. But for example, if you want to do it in higher dimension, for example, where the bulk dual is like CFT3, then there will be a fixed point, and that means there will be a singularity at the tip of the cigar geometry. And the hope is that probably if you embed CFT in some other thing, string theory or something, the singularity would get resolved. But just staying within the CFT setup, you don't know how to resolve that singularity. So that's one comment. And another comment is that, like this relation I wrote down here, it follows from this stacking procedure and just evaluating the effective action manifold. That at this point of this manipulation, that doesn't really depend on whether we are dealing with the CF. So, and so if you start with a massive QFT, so the first thing we need to change that instead of beta going to zero limit, it's better to think about L going to infinity limit, where you take the spatial volume to be very large. And in a massive QFT, because it's not scaling, so the beta going to zero and L going to infinity is not same. So everything should be in the massive QFT. I should be stating everything in terms of L or the volume going to infinity limit. And in that limit, we do the same kind of stacking procedure. And again, we can write down expansion of this, like write down an equation of this form. Because now it's a massive QFT, then we have to be a bit more careful about how we can expand this on the both sides. But as an equation, like as an equation which relates to different kind of partition function, is true even for a massive QFT. And we can explicitly again check this for a take a massive scalar field theory, and one can compute both sides explicitly and check that it works. And it also could be the case that if you to zero limit and take Q to be large, then there can be a scenario where sides of the equations are in a different phase, and then this equation will tell you that you are relating quantities in the different phase. And so in that sense, this is a much more general result. And mhm, mhm. Yes. Oh yeah, that so the yes, exactly. The coefficient would be different on both sides, but there would be a relation. So and I guess a nice way to check this is to just take the massive quantum field theory and take the m going to infinity limit or m going to zero limit, and then we'll see how things match. Oh, I see. Yeah, that's not really interacting too, but I think the essential features are same. But definitely, in the case of CFT, one nice thing happens that the same Wilson coefficients appear on both sides with some scaling. So that's a huge predictive power. But for a massive quantum field theory, this relation is true. But then because this, if the two sides in a two different phase, then the coefficients might be arbitrary. Like they happen, but there is no order by order expansion in that sense. Okay. So just to recap or to say read the main point of the story, the following: if you consider a generic CFT, either fermionic and bosonic, just have to tell me two quantities. One is trace or minus beta h, or minus beta h minus 1 to the power a. So in the beta going to zero limit, both of them will give you sets of Wilson coefficients. And once you know this set of Wilson coefficients, you can predict if this form with or without the insertion of 1 to the power a. And in higher dimension, there can be genuinely new contributions is defect, and but their form is also uh, constrained by the tree and the EFT idea. Okay. Mhm, 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 mhm. See. Mm, mm, Yes, yeah, I don't have anything to say about non-existence of such manifolds, but definitely this one on the nose basically gives you the right answer. Uh, Oh, you are worried about some contribution coming from the singularity or? Hmm. Yeah, for example, in S2 time, yes. Well, in ADS3, there is no singularity. Yeah. Yeah, in particular, when the boundary is S even minus S1, there will always be some singularity. But in area, it's just a SL2Z image of the original thing. So it's a all well-known solution. Yeah. Yes. Yes. Something like yes. Yeah, but I don't know how concretely this like, but you would need more stuff, right? Like you just cannot do it. Yeah. But that works at space, right? But here basically the tricky part is here you have ADS, so you might hope that near the singularity, if I look very close, is almost like flat and do the same procedure. Actually, we thought about this a bit, but never made it very concrete, like because it's a ADS, so yeah. Mhm. No, I think the correct mathematical statement is if there is a irrational angle and if you take the beta going to zero, that limit doesn't exist. And another way, physical way of saying it, as Nathan was pointing out, that basically for some irrational number, you basically hop from one EFT to another EFT. Mhm. Oh, oh no, I would think that so there are irrational numbers for which like you basically cannot even see this EF this hopping behavior. Like for example, golden ratio, I think. Because it's like the continued fraction is all one, 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 one. And my take is from I think my take is that like this is another way of saying that this limit doesn't exist. So precisely because of like if you like depending on how you are taking the limit, you are basically hopping. So hmm, yeah, no, 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 yeah, yeah, hmm, yeah, sorry, when I said non-existent, I meant that it won't be universal across CFTs. It will depend on the state. Hmm. 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 But yeah, 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 yeah. Granted. Yeah, from word line. Oh, that's another thing. Yeah, those are basically some, because it's a massive QFT in the SD minus one. You can think of some word lines with some mass moving around, and you can evaluate the word line action, and that will give you some contribution. Yeah, and theory is basically you can write down everything because you have the, it's a matter of expanding. Mhm. I think Nathan is going to discuss this. I think it will fix, like, if you take a, like, black hole and expand, like, compute the free energy, or then basically it will fix all FC1, or probably the ratio of this. Yeah, yeah, mm, yeah, yeah. Whereas in 2D you only have to match the central part. That's, yeah. Yeah, yeah. Oh, in term, I guess it's well, of course, in the sense of all these transformations, basically gives you a proxy for this the transformation in 2D because you are in the same field of information. So in that sense, it depends. So by modular symmetry, if you mean SL2Z, then I don't think so. And but Well, I guess here, well, I mean, the when I say that it's a proxy for modular symmetry, modular group is all I mean that like this path integral manipulation you do, it captures the same kind of information that is captured by some modular transformation in 2D. Like there is, you have to do, yes, then you have to do S1, some different manifold, S1 times S1 times S1, then of course. Oh, I see. No, I think, no, I think it's not related to that. No. Yeah, yeah. Yes.